Okay, hello everybody. How are you? I'm happy to be online here with you for this first week, the webinar, this first week, Intro to Computer Vision, Filters, and Edge Detection. Um, I hope you can hear me all right. I don't think I have any viewers yet. Uh, I tested this, I was testing it. It seemed to be working fine, the sound and everything. I'll go on. If you log on and you can't hear me anything, just tell me. You can write the you can chat in the YouTube chat or write on Slack. And anything you need throughout the whole presentation, I'm going to be checking the messages, and I hope we'll have a lot of fun together. So um, let me see. Just starting off here. What are we going to do today? We're going to talk first about the introduction to computer vision, some of the applications, common applications or stuff people are doing right now, and then we're going to go a little bit more in depth into image representation, filters, and edge detection. And then after that, I'll have a time for questions if any of you are online during the live webinar. If you're not live right now, then you can just send me your questions through Slack whenever you log on, and we can go through those questions there. Okay? And the questions can be about the content, the introduction to computer vision, image representation, filters, and edge detection, or it could just be about the nanodegree as well. Support services, the projects, classroom, anything. So let's start off. First of all, some intuition. First things first. Why? My first question is, why do we even need computer vision? I think most of us can agree that computer vision is actually a means to an end, not as much an end as in itself. So we want the machines to do something intelligent. We want them to do something. And Stuart Russell, Peter Norvig, they define intelligent agents like any device that perceives its environment and takes action that maximizes its chance of success at some goal. So basically, this definition makes it quite clear. We want the intelligent agents to act, to do something. And for that, we have to allow them in some way to perceive their environment. To successfully reach their goal and act, they have to be able to perceive their environment in some way. And here, perception leads to action. And computer vision is one of the many ways, one of the many tools we have to help machines perceive. And there are many ways to do this. We can use different types of sensors, IoT devices, manually tell the machine and everything. We can collect stuff like temperature, GPS location, speed, a lot of stuff. But there's something very special about computer vision in itself. It has several benefits, and I'm going to talk about two of them right now. That's first of all, cameras are relatively cheap and almost omnipresent. I mean, there are cameras basically everywhere. And don't get me wrong, computer vision is not only useful for cameras. You can use a lot of basically the techniques and methods you're going to learn throughout this nanodegree will be useful for you. You can apply it to basically any spatial information. So, for example, input from a LiDAR sensor, for example, or anything else that has spatial information. The methods you're going to learn here are perfect for that kind of information. But the majority of projects we will be working with, I mean, all of the projects in the nanodegree and in the real world, most of the projects you will be working on will be using input from cameras. It could be phone cameras, it could be professional cameras, it could be industrial cameras, it could be just pictures, video, but in the majority of cases we'll be working with cameras because they're relatively cheap and they're omnipresent. I mean, there are a lot of different types. And the second benefit, which I like a lot, is it gives us a common ground to communicate with the machines. It kind of gives us a similar perception. here, when I'm talking, our communication is quite efficient because we have English as a common ground. If we were all to speak in our own languages, if I were to speak in Swedish and you guys wouldn't understand me and you try to respond in your own language, and if some of you speak some other language, it would be quite inefficient and it would be very difficult for me to explain technical concepts. So there's something very special in being able to see similar to what the computer sees. So I can tell it, I can understand better its position and tell it what I actually want from it better. In terms of some applications, this one's quite cliche, I know, autonomous cars. The reason I'm showing this is because the image, it has one of the different computer vision tasks that you'll probably be using in the future, and it's image segmentation. And you'll be able to use it not only for autonomous cars, but for many other uses as well. A second very common application is image classification. And if you've been through the first lessons in the classroom, you have probably bumped into the day and night image classification task. It's quite a naive classification task because you're basically hard coding a rule according to one of the channels of the image, moving it over to HSV space, which we'll be talking about a little further down in the webinar. But the reason I'm showing this one is because just to show you a real world example of something that isn't very hard, isn't very complicated, and you can get very it can have great implications and very useful for the people using it. So here's a person that built an invasive plants classification. The image source is there in the presentation. I can share it with you later if you want to just check it out. So they collected a lot of images about harmless and invasive plants, and we can understand how this can be super useful for agriculture or for anybody who has to work in nature with this kind of stuff. It doesn't take huge amounts of data to get some, depending on the scope of the project. But this is just something very useful and something that doesn't require a huge amounts of resources to do. So I wanted to show that. And the next one is one I like a lot because it's creative uses of computer vision. And you may laugh at me because of the next picture, but I basically, many of you probably have heard about style transfer. It's basically being able to copy the style of an image, for example, a painting of a famous painter, and use this style in another image that we have taken ourselves. This particular project I worked on here is based on a paper called Deep Painterly Harmonization. So basically what it allows us to do is not only copy a style and use it in another image, but we can basically just copy a style to a specific part of an image. It's not the whole image itself. So here what I did was I cropped out my face in a picture, and I had seen this other painting online, and I said, this painting is cool. I would like to have a painting of that for my own. And I just cropped my face, used the techniques in this paper, Deep Painterly Harmonization, and in basically 5 minutes, it took a while to construct the architecture and the notebook and everything, but training really just took 5 minutes. And yeah, for some of you this might not be as impressive, but for me it was just mind-blowing that in 5 minutes I could have literally a painting of myself as a general that I could have had to pay maybe a lot if I've asked a painter to do it for me. So this is super awesome and great use cases as well that you can find online if you want. And yeah, that was kind of it for the intro. And with this, we'll jump over to image representation filters and edge detection. And for this, I'll be jumping over to a Jupyter notebook. And start with, of course, here loading the imports. Sorry, it doesn't seem to. Okay, no. The image. The thing is, I was watching the feed in another screen, and it seems to be a bit behind. So I got scared that maybe it wasn't popping up, but it should pop up shortly. So where I start off is imports. I usually recommend, it's a good practice, but it's not mandatory, that you set the imports in the first cell of your Jupyter notebook. And as you're working down the notebook and start importing new stuff, I would personally recommend that you add those imports to the first cell. This has several benefits. One of them that has happened to me several times is that sometimes I add imports further down in the notebook, and then throughout the project I'm experimenting with the notebook, experimenting with the project, and I decide, okay, no, I don't need this cell. I delete the cell, and then I restart the kernel and I start working again, and then suddenly stuff breaks and doesn't work anymore. And it turns out the import was just was inside the cell I deleted. So it's just a small detail, but it gets a bit tedious when you bump into these kind of small problems, and you're focused and you want to go fast and you want to get it all to work. So my recommendation is that you keep them on top, and you just avoid. It's just a very easy way to avoid this kind of problems. So yeah, let's load the libraries, and first of all, image representation. So I didn't mention OpenCV is a library specifically designed for computer vision tasks, and it's free to use under the open source BSD license, so you can use it for any projects you want. It's super useful. I'm going to load an image here. Start by loading an image. With OpenCV, you can do it very easily with the .imread method, and you just give it the path of the image. And the first thing I'm going to do is print the image shape. And this is something else very useful. When you load the image, this image object will have different methods and characteristics you can use to just describe it and everything. So I'm going to print the shape, and the first thing we see here is 1280, 793, and 3. So printing out next here is what this basically means is that we are now working with a matrix, with a multi-dimensional matrix. So it's just a bunch of numbers. This is all we're working with when we load the image to the computer in our workspace. And basically these numbers we see here, I think you should be able to see my mouse. These values you see here are the pixel values, and for each channel it's giving us the value for that color in that channel for each pixel, and the range is from 0 to 225. For some of you, you maybe already know this. This is super basic for most of you, but maybe some of you don't. So I'm still mentioning this, starting off pretty basic, and you'll see this nanodegree. It goes really deep, very fast, and we'll be going into quite advanced algorithms in the future, and techniques, Kalman filters, and object tracking and everything. So if this is too easy for you, don't worry. You can just skip it and move forward. And for the rest of you, I'm just going to keep going through this. No problem. The idea is to help everybody in this process. And we have the one-on-one calls and AMA sessions, private messages, anything to make the experience more personalized according to your needs. Here, I'm going to print the type of the image. This shows us that we're working with a NumPy array. NumPy is a library we can use with Python that makes working with arrays and numbers super easy and super efficient. And this little image I'm showing here is, I'm a very visual person, so it's useful for me to be able to see stuff. And so that's the reason I'm sharing with this, if there are any other visual people out there among you guys. And basically the image we're loading, here we have one of a cat. I loaded another image above, you're going to see it soon. And basically what we have here are 3 channels. And here you see blue, green, and red. And the same thing here. This is just another representation. This one's the blue channel, the green channel, and the red channel. And as I mentioned earlier, each one of these is the pixel value for that particular color in that pixel. So here we can see that this kind of corner pixel has a value of 4 for blue, a value of 9 for green, and a value of red of 35 for red. And those colors get combined, and that's what we see. Kind of like how our computer screens and everything work. Different colors, and they get mashed up together with different intensities, and that's how we build all the other colors and how we see everything. So knowing this, I'm going to now print out the image so that you can see it. And for this we can use matplotlib. Sometimes the images, when you print them out, I'm showing it here, they might be too small or too large or anything. So you can add this argument, which is super useful, and it's just the figure size, and you can just set here the value you want. And plt.emshow helps us to print out the image. I loaded it up here as like this. Import matplotlib.pyplot as plt. That's you don't have to load it as plt. It's just common practice. It's what basically everybody does, and it makes it much easier if you keep that standard when sharing the notebook with anybody else and stuff. So printing it out right now. Okay, so something seems a bit odd here. I'm going to zoom in. I got married 1 month ago, so that's all I can think about right now. Super happy, love my wife. But I promise you guys that my skin color is not blue. You can see it in the webcam down in the right side. My skin color is not blue. And it wasn't blue on my wedding day. So something's wrong here. Something's definitely wrong. And to know what it is, we can go back up here and see the 3 color channels. And here we see the order of these color channels is BGR, blue, green, and red. The reason this is like this is because OpenCV loads the image and sets the channels in a specific order. But it turns out that matplotlib, when we want to print it out, it expects the same channels but in a different order. And further down in the line, when we start working with PyTorch and as a framework and start loading images, it turns out that PyTorch expects the images in another way as well. But this time it's not the order of the channels, but the order of the dimensions. So we'll be going from having the image dimension. Let's see, let's go up a bit. Here you saw that the color dimension, the color dimension is in the end. It's the 3 here in the 3rd dimension. PyTorch will expect it to be in the front. So that's a very common mistake that often happens. So if you load an image, print an image, and see that visually it looks wrong, it seems like the color are inverse or something, definitely try checking which library you use for loading the images, because other methods, when you load it, you can load an image as well with matplotlib. So when you load it with matplotlib, you might have it in RGB right from the start, and you might need it as BGR for something else. So just so you have that in mind, that's a common issue that happens a lot. So how to fix this? OpenCV has a very useful method called CVT color, which we will be using a lot, and not just for this BGR to RGB, but to changing it to other color spaces like HSV, hue, saturation value, or to grayscale, and specifically grayscale. We'll be working a lot with grayscale. So I'll just fix my image here first. And you'll see me in my full splendor. Not me, I'm just kidding. I wasn't so special that day. My wife in her full splendor on her wedding day. And that's the colors, the real colors we had back then. And we can use that, as I mentioned, that same method to convert the images to grayscale. And I printed out the shape here. So now it's just one channel. So we don't have the third dimension anymore. It's just one dimension, and it tells us the intensity of each pixel, because now it's just going from black to white. Each pixel is just going from black to white. So 0 is black and 255 is white. And it just gives us the intensity for each pixel, and it looks like this. The question now is, why is this so good for us? The reason this is good for us, that we are working with numbers, is that we can start making we can start using math. We can just start using math to get what we want. Basically, I'll start with something super easy. The math is not as important. You can just see here that I'm using NumPy that I imported earlier. Import NumPy as NP, and a function NumPy has called average, and I'll just be taking the average of each row in the color image, not the grayscale image, but the average of each row, and I'll be showing you the average color of the whole image. This is going to look like, okay, the values 136, 34, 81. Which is the color in each of the in each of the channels, and when I print it out, it's going to look like this. And if we see this color here, and we move up all the way over here, we can definitely see that it makes sense. I mean, it makes sense that that could definitely be the average color of the image. And this gets super interesting, because this way we can start just using math to get information we need from the image. And before I take it up a notch, I just want to go through with you why this is so important, or this is so useful, that we can take that we can use math to start looking at different things that the image has. So I'll be switching over to me. Hello. And as I mentioned to you a little while ago, I got married a month ago. And before that, we had several parties, let's say, that I didn't organize. Our friends organized and my family organized. And they would give us a lot of gifts. We got a lot of gifts. And I don't know in other cultures specifically, but here in Colombia, it's a very big deal that when you get a gift in the weeks coming up to your wedding, you get the gift, and the whole idea, and I mean, people think it's very special that you try to guess what's in the gift before you open it. You always have to guess, and my wife is an expert on that, not me. I'm not very good. So I brought one of the gifts. Well, actually not one of the gifts I got there, but let's imagine. And it's basically this one. This is a gift I got, and I have to guess what's in it. And as I mentioned, I'm not an expert. I'm not very good at this. So you guys are going to help me. whenever you're watching the webinar, so you can, yeah. I'm going to start by checking it, because that's the sound is a useful thing to know, but you guys, if we're just using vision, something we wouldn't have. So I opened up a few slots here that will help us to see hints about what are inside, what could be inside. And the first one I'm going to open, will be this one. And it basically shows us, I would say nothing, but this is not nothing. This is white. And white gives us information. What gives us, I mean, we as people with experience, we can start guessing and we can start saying, yeah, it could be a book cover. It could be, yeah, a white paper, maybe. It could be a paper. Could be a white box. Don't know. Gave us some information. We have at least taken away a lot of possibilities. It's not an elephant. It's not a scooter, not a car. The size, yeah, definitely not a car. But yeah, we've narrowed down the possibilities a bit, but still very far away. So if I open up this one over here, we're getting some more information. This is different. This is a corner. So yeah, this could still be a book and could still be a box, but looking more like a box maybe. Definitely not a paper, because it's possible to see a bit of depth over there. So not a paper, and a corner. And no, I'm not going to stretch this out anymore. I'm going to open up the last one, and this one will probably give you the information you need. Okay, it's a tablet. Basically, this is a box for a tablet, and we guessed it mostly with this one, but the other twos, and yeah, basically the package shape gave us the information that it was a box. The whole idea with this, it could be maybe a bit childish for some of you, but it teaches us a very important lesson. And the thing is, as people, we use our vision so much every single day that sometimes we end up forgetting how powerful and how it is and how it actually works. When we see stuff, our eyes take in a lot of information, a lot of data, a lot of information. And we take it up all at once and we use it all at once. And that's the reason I say we forget a bit about how powerful it is and how it works. But if we break it down, the thing I did there was break it down into 3 steps. And it gave us different parts of information that we needed to make the final prediction of what it could be. And this information, we will be calling them features. And one of the features is that it was a white background. Okay, we're watching something white. One of the features was a corner, and that was quite useful. I mean, I'm using a video here, so you could obviously see some of the spatial information in 3D. But if it were an image right straight from the front, you wouldn't know how deep the package would have been. So you would just have been able to see it from the front. And let's say that the package, I mean, the package gave it away a little bit, but let's say the package was different, and let's say the package was circular, and I opened it up there and it was a corner. So the corner gives us more information. It tells us, okay, it's white, it has a corner, and then when we open up the last one, we see something very familiar, and it's the form of a tablet. And that gave us all the information we needed to say, okay, that's a box that contained the tablet once. That is actually, I don't know why I still have it, a tablet I bought in 2011, but it's a box with a tablet. And with that, I'll jump back to the notebook. Let's jump back to notebook. and talk about how we can use math with the images to extract features. So when you've been going through the lessons, you will have heard or you will have seen that one of the main things we want to do when working with images is that we want to know ways and that we want to learn techniques and methods to extract the useful information that we need, those features, and ignore the irrelevant information. There could be noise, background noise, there could be a lot of things that we don't care about. We don't want to know anything about that. But we want to get the features that we find important. So with that, we'll move down here and we'll take the computations up a notch. So basically what I'm going to create here are a few, let's say, filters or kernels, and I'll call them filters because they'll be filtering out information further down. And I'll print out this first one. I call it a mean kernel, and basically it's a mean because it's 25 values, and if you sum them all up, you will get 1. So if you take these 25 values and multiply them with another set of 25 values and sum everything up, you will get the mean out of that operation. And I'll show you this specific kernel applied to an image, the same image above but grayscaled. So I'm going to zoom in a little bit here, and this blur, it's not because I just zoomed in the image a little bit, but this blur is actually caused by the operation we just did. I took basically this kernel and I multiplied it and summed the value for each of the pixels in this image, and that gave us an average value. The pixel, basically we were calculating for each pixel the average of that pixel and all of the values around it, basically, and that's why it causes it to blur up a bit. And what is actually happening here is this. So okay, let me just print out here and print out this example. Basically, let's say this little square moving here is the matrix I created above, the 25 value matrix with every single value being 0.04. Let's imagine it being this thing. So we're going through and the background here would be our image. So we're going through and we're calculating this new image over here during the calculation. So as you can see down here, if we just take this first part, the first operation, we will be going, this is our example filter, the one moving around. Let's forget the mean kernel above for just a second. Here you can see 0, 1, 2, 2, 2, 0, 0, 1, 2. It's the one moving around. And then behind that we have the values, okay? So let's just take this first square over here, and if we do that operation, we multiply, and sum all of them up, we get 12. And we do that for every single pixel in the image. But we have a small issue, and this takes us to something that Joe asked me about, which I will show you right now. And it's when we go through this, the resulting image, or the result here, is smaller than the input. I mean, the output is smaller than the input. And this will be something that you will be using a lot when we go down to the convolutional neural networks. When we get to convolutional neural networks, you will be using this knowledge a lot, because this will define how the shape of your image changes throughout when it goes through the network from start to finish. So if you just apply a convolutional kernel to it, like this, it's convolving, moving around it, So if you apply this to this filter just like it is, you'll end up with a smaller image. And this can be a problem sometimes, because if our network is very deep, we will start off with a normal image, and in some cases our images are quite small because of the computational complexity. So let's say that we start off with a 32 by 32 image, and it gets smaller every single time. Here it's basically half. Yeah, here in this example it's half. So if we go half each step, each time we have a convolutional layer, and we apply this this kind of a function to it, then we will run out of image to work with very fast, and we won't be able to go very deep. So how do we solve this? And this is where I go with Joe's question. He was asking me about zero padding and the purpose behind zero padding. And this is something that is quite difficult to understand sometimes if you're starting off. When we're starting off, it was definitely difficult for me. Not just the purpose, but how we calculate the size of the output. So because here we work with output, with zero padding, and then you'll see later on that we'll be adding other parameters like the stride, which means how much it's jumping in each step. Here we're going 1 pixel each time, but we could be going we could be jumping over a pixel each time and just doing 2, or we could be jumping over 3 pixels differently. So, and that gives us different results. And all of that is stuff you should be able to calculate and know, so that you don't end up with a wrong shape in your inside of your neural network of your input. So basically what we did here is that we added pixels around our original picture. So we have our original picture here in the middle, and we added a padding, let's say, of zeros. So this 0, 0, 0, 0, 0, all of these are zeros. And what ends up happening here is, if we use this same example, I'll be using this one, so we can see that the square up here is 332, 001, 312. And if you see where it starts, it calculates this pixel over here, this one. But let's say I want to start over here, because that's what I need to get a pixel over here. Then I want to move over to this one, so I get a pixel over here, and all of that, so that I get the original size. But I can't do that right now, because if I try to start my kernel over here with centered over here, then it won't have any values to calculate with over here, and it will give us an error. And that's what helps us down here with a zero padding. The values we'll end up using would be 0 over here, 0 over here, a 0 over here, and a 0 over here. And inside 0, 0, 0, and 3, 3, 3, 3. So moving down here, I set it out for us. So most, as we just saw, most of them are zeros, and we still have our filter, or our kernel. It's 0, 1, 2, 2, 2, 0, 0, 1, 2. And as most of them are zeros, the only value that we end up using is this one specifically, which ends up being 2 times 3, which is 6. So the value we would be having up here would be 6 in this pixel. And that's basically the purpose of zero padding. And this is kind of, a very simplified way of how the math would work. Very simplified. If you want to go deeper into the math, we can do that privately. But just to give you a first intuition, we will be going through this in more depth later on when we get to the convolutional neural networks and strides and everything. If you don't quite understand some of the concepts I'm mentioning, don't worry, you will bump into them later on. So just for you to know right now, this is basically the operation I'm doing right now. There are other ways to solve this, but this is a super simple way. There are other ways of solving the problem of keeping the image size, but for now one we will be using in the convolutional neural networks is this one. Very efficient, very useful, and quite easy to understand once you see it. At least for me, when I see this visually, it becomes much easier for me to see how the math works and everything. So now I'll be creating a new kernel, and it's this one: -1, -2, -1, 0, 0, 0, and 1, 2, 1. And the reason I'm doing this is, as I just showed you guys with the box, is we want to get features out of our pictures, and we want to have useful information. So let's say in this image, my wedding, this was my first dance. Let's say I would like to identify where we are standing as people and where the DJ is standing. I would just want to have this basic information about where we are and yeah, maybe the stand behind, but I don't really care at all about maybe a glass standing over here, a light over here, I don't know, napkins, this little cloth on the table. I don't care about any of that. I just want to know maybe how many people are in the picture. Maybe that's my question. How many people are in this picture? So we want to filter out the unnecessary noise and just keep the unnecessary information, which is basically noise for us right now, and just keep the basic important information that we want. So that's what we're going to now, which would be edge detection. There are other ways we can do this. There are other methods, and there are obviously other features we will want to have, not just the edges. But for now, for today's webinar, we will just be going through the edges. And one of the first steps, which I already did, and I didn't, just went past quite fast, I'm going to go back to that right now, is the fact that I turned it into grayscale. So why is this important? If I want the edges of the image, then we're dealing with another set of unnecessary information that I was carrying along. So over here we have an image that is full color and it's complete and everything. But when we see the shape, basically what we can do with this shape is we can get the total amount of pixels we're working with by multiplying these three numbers. That's the total amount of pixels in this matrix. 1280 times 793 times 3. And that's quite a lot of numbers. Especially when we're going to be doing math operations and we want to start doing stuff with these numbers. And then we start thinking and say, but hey, wait a minute. I just want to get the edges. I want to know where the edges in the image are, where the pixel the intensity of the pixels varies very strongly, because that usually means that there's something important there. I don't care about this part. I mean, this is very homogeneous. I mean, super similar, all of this. I don't care about that. I want to know what happens over here, because this is something new. Or I don't care about any of this over here. I care about what is happening over here. This is something special. As well here, when it changes from white to something here. So this would definitely tell me, okay, there's something here happening here. There's something there. When we just see plain information like this one over here, basically nothing's happening. If we do care, I mean, just jumping to another example right now, if we want to know where this platform is instead of the people, well, we still don't care about this part. We might care about these edges of the platform, because these gives us the shape of the platform, and we get kind of a squared, which is warped a little bit because of the perspective. But if we get these edges, we can basically say, okay, that's the square, and it's a bit warped. That would definitely be the platform. But we don't care about the information inside. So edges are a very powerful way, a very powerful feature to get information from images. And thus color doesn't add anything at all. color is just, in this case, it's just noise. In other applications, color can be super useful and almost critical, but in this case, just noise. And we want to, and for that reason, we can just take it away and keep this very smaller matrix, which is now just 1280 times 793, much smaller, and that means that computation is much easier as well, less expensive. And okay, for one single image, not very important, but when we're working with neural networks and we're going through thousands of images at the same time, yeah, we want to train with thousands and thousands of images, maybe even a million images, then computation, how expensive our computation is, quickly becomes very important. So I'll be moving down here again. So that's why I created this kernel here. And what it does is basically a gradient calculation step. And it detects the intensity and the direction, basically, by calculating the gradient of the image using edge detection operators. Okay, changing the words a bit, it just gives us a way to know how the pixels, the pixel intensities are changing in a specific direction. So here, if these values are very similar to these, you can imagine this just canceling out. So let's say we have this is 3 by 3. Let's have another one that's also 3 by 3. Another that will be multiplying by this. And let's say that this first row, it's just 10, 10, and 10. No change at all. So this 10 is going to be 0. And when we sum up this one and this one, this will just be minus 10 plus 10. That will be 0 as well. So that it will just give us back a 0. But let's say this is maybe 0 and this one is 100. Then we'll be getting 0 times minus 1 plus 0 plus 100. And that's 100. So we can know that something is changing there. And that is what we'll be seeing in this image over here. Doing this same operation, going through and calculating with this new kernel throughout the whole image, we get this particular image. And this is quite interesting. If you see here, we're comparing the pixels vertically. I mean, this one and this one, and to see how different these values are from each other on this side. So here, as I mentioned earlier, you can see this bottom part of the platform, which is very similar in all of the pixel values in the image. It's basically just black now, and the white lines we get are the ones that where there were notable changes. If you remember here, it was quite white in the background, and my clothes started off over here, and so this was a very big change. So it gets very white, and here especially over here, the platform, and then the dress started, which is very white, and that's why we get a very marked line over here. And then all of this inside over here, it was just white as well, so it gets turned black. So we filter out a lot of the unnecessary information. And this particular filter gave us all of the vertical lines. So we can do the same thing in the other direction as well, horizontally. We can compare the lower pixels to the pixels above and get something similar as well, but horizontally. Here. So now you see, now it doesn't really care that much about my legs, for example, but it does care about my arm, which is basically almost horizontal. It cares a lot about the lines in the background, and this helps us to get this person over here, thanks to these lines over here. And this also picks up a few lines and everything. So we see that different calculations and different techniques we can use give us different features and different information. This arm is barely visible over here, and my legs are barely visible in the other one. So we can take smaller steps and build them up together to get something much more impressive and important. The thing here is we're still getting quite a lot of noise, and specifically our lines also turn out being noisy as well, because some of the lines are very, very wide and big, and some are very, very small and almost imperceptible. And we just want the edges. I mean, we don't want to know, we don't want something super huge or small. We just want to know how it looks, the edge. And for that, we'll be using something to detect the edges. You'll be using something which is called Canny edge detection, and it does basically the steps I've been going through over here. Basically, we apply it to a grayscale image like this one over here. We blur the image, and the thing we get by blurring the image is that we reduce a bit of the noise. By blurring, as you can see, we care about these things, but suddenly by blurring out, suddenly for example, my beard, it's not as defined as earlier. So we don't really care if we can see each of the hairs in my beard. We don't care at all. So by blurring this out, it just turns out into kind of a blob over there, and we end up getting this feature, which is where the beard starts, and maybe this feature, which is where the beard ends. And to that we apply what we call Sobel filters, which is very similar to what we just did over here, which are these and this. And we use all of that information, and then we simplify everything by using something called non-maximum suppression. And the idea here, ideally we want to have very thin edges, and that's what we can do with this step. And